out Alex, because it was his slide, but he was in a previous slide, and Sima Luft Maranglu is our new PhD student in our group, and Jack Crystal is undergraduate, and Yusuf undergraduate, but graduated last year. So this is our first paper on positron annihilation-induced Auger. Was our letter 7. Principal advantages of studying surfaces with positrons, and specifically positron Auger, is very high surface selectivity. So we have one of the highest selectivities for the top layer of any surface spectroscopy. Another thing is very low background, and may show you some stuff later that makes use of that effect. And it's also selective for nanostructures, and as we'll show later, the selectivity can help you study internal surfaces. So the positron annihilation-induced Auger process is shown here. I don't really know how to do the animation, so I hope it works. I did have to do some modification to see if it works. But a positron comes in from the left. What's shown on the right is an energy level diagram. So let's see. Okay, so the positron comes in. This is an energy level diagram. These are core levels. These are electrons that are close to the nucleus, so they take a lot of energy. Let's say in carbon, it takes about 250 electron volts to compare to visible light, which is 4 electron volts. So it takes a soft X-ray or something like that to get these guys out of here to eject these electrons. And what we're going to do is use a positron to tunnel in there and annihilate with that core electron. And you get a hole. And that hole represents a lot of energy, because that hole can be filled by a less tightly bound electron, and the energy transferred through a virtual photon to another electron, which can then leave the surface of the material. And because the energy levels of all these of each element is in general unique, and especially these core levels, like the core level we look at in carbon, the 1s is a binding energy of about 300 eV, and oxygen is like 500, and in copper it's like 80. So these core level energies are unique, and so by looking at the energy of this outgoing electron, which depends on the energy difference between these other valence electrons, we can figure out what elements are. All right, so and the surface selectivity comes from the fact that the positron gets stuck on the surface before it annihilates. So if we inject the positron into the surface, into the material, it'll pop back to the surface and get stuck in an image correlation well. And this is some theory that was done by our colleague in Alex Weiss, and who unfortunately passed away. But he worked with us on developing this theory. It's a one-dimensional, a single particle Schrodinger equation that you get for the potential of a positron sitting at the surface, and you solve that for the wave function. You get a wave function, and you do a detailed calculation of the overlap of that wave function, the positron wave function, with the electron wave functions in the material, and you could show that 95% of the annihilation takes place with electrons in the top layer. So this is what gives us the surface selectivity. So the positron comes in, it diffuses around, comes back to the surface, gets stuck in the surface layer, and then it annihilates in short time, 10 to the minus 10 seconds, leaves this very excited atom at the surface that emits an electron in very short time, 10 to the minus 14 seconds.
So we have a quick question for you. Someone asked, the Auger electron is ejected so as to ensure momentum conservation. Is that correct?
Well, actually, it's this equation relies on energy conservation, and so the momentum is conserved when the electron leaves, because the nucleus takes up the momentum, or and when you have a solid, it could be that the entire solid takes up the momentum of that outgoing electron. And we once had this question fairly recently. A few years ago, we submitted a paper, and this is a non-trivial question of momentum conservation. And the referee in the paper said, "Okay, but did you conserve momentum in this process?" And I didn't actually write this back to the referee, but I said to the group, I said, in this lab, we always conserve momentum. It's a rule. We don't. So yes, momentum is conserved, but sometimes it's not that easy to see how, and sometimes in solid state, the momentum is taken up by the whole lattice. But you have a lot of atoms around, so if the electron comes out with certain momentum, the momentum of the whole crystal picks up momentum in the opposite direction. So the total momentum, if it started at 0, ends at 0. So we measure the energy of these electrons by looking at the time of flight. So we get this nice annihilation signal, which just tells us when the electron leaves the surface, because after the annihilation takes place, the electron is gone in 10 to the minus 14 seconds. So basically, we're measuring things at time scale 10 to the minus 9 seconds. So it's essentially instantaneous that the electron leaves, and we detect the gamma ray, and then we have a several meter flight path and detect the electron at a later time, and then we measure the time difference, and then from the time difference we get the velocity, and from the velocity we get the energy. And that's a picture of our original beam. This is in Science Hall, and we just built a new one in CPB. And this stuff was designed and built by graduate students and undergraduate students here at UTA. And so this shows you the peaks that we get in the time of flight distribution. This happens to be a dirty copper sample, and you can see all the different peaks corresponding to different elements. And here is converted to energy, and so we can interpret what these peaks are in terms of the energies of different elements associated with different elements. All right, let's see. I've used up 19 minutes. I think my screen just died.
We can still see the electron energy spectrum slide.
Oh yeah?
Yeah. And still see your laser pointer. Yep, still looks good on our end.
Yeah, so it just it went into some spinning disk mode on my part. All right, so we did experiments which showed that you really do get surface selectivity. This is one done by Alex Weiss, and we showed that by putting a single layer of palladium atoms on the surface and then heating it up and watching them diffuse in, we could see that we got a peak from palladium when it was on the surface, and we didn't see any copper. And then when we diffused it in, we started to see copper, and then when we diffused it in some more, we saw only copper. And then with the electron Auger, which is another way of doing it, competing method, it's very hard to tell what's on top, because you see copper and palladium in each case, and this is because the electron Auger is stimulated. The core hole is made by an energetic electron beam which penetrates many layers, and so you're averaging over many layers, so you don't get that surface selectivity. And we use this to look at topological insulators recently, and these are also thin films. this is animation by Alex Weiss, which is cool. So I'm just showing the same thing again. There's the palladium on top, and there's the, you have to heat it up. You get mixed palladium copper surface, and you get two peaks, and then you heat it up some more, and the copper comes on top, and you get only the one peak from the copper. This is carbon atom. So this shows you what happens with a monolayer of graphene. So one of the things we've done recently is look at a single layer of graphene carbon atoms on the surface in an ordered system of graphene. And because our positron is so surface selective, we can look primarily at the graphene and not at the substrate, which other techniques can't do. So we reported the Kaushik from this graphene recently and observed a transition that had never been observed before. So this shows the theory of, again, the positron wave function on the surface of graphene, and that was in Nature Communication recently, and Alex Weiss was first author on that. And I'll go very quickly on this, but another feature is that you can get rid of secondary electron background. Secondary electrons, due to the incident beam, is a big problem in electron spectroscopy. So this shows the secondary electron peak, and we're going to lower and lower beam energies, positron beam energies. And when we get down to beam energy of 1.5 eV, we can get rid of the secondary electrons altogether, and what's left is just Auger electrons. And secondary electrons are typically unwanted. So in the secondary electron, the incident particle comes in and just exchanges energy momentum with an electron and kicks it out. Let's see, how can I do this slide? It seems to have a little bit of a mind of its own.
Yes, such is the will of Microsoft products. We seem to be stuck on that.
I have 12 different screens open at once, so this is probably why. There we go. So this was done so we reported this in Nature Communication recently. This new transition in graphene that had never been observed, and basically what happens is you come in, the positron comes in and annihilates with an electron in the valence band, and that's what was new did the valence band. And the valence band in graphene is very deep, it's 25 eV deep, and so if you make a hole at the very bottom, an electron can drop down, and that gives you enough energy to leave. And so this slide, I reformatted the slide, didn't quite work. But anyway, that's one of the fun things about what we do is that typically the experiments we do are new and unique. Other people haven't done them before, so we have to develop our own theory. And we work with theorists, and this is the theory we developed of this particular transition. And it was involved a lot of integration and convolution over densities of states, and this was a theory developed by Charayeth and our colleague in Belgium, theoretical colleague in Belgium, who did a lot of the calculations, but we actually worked with the theorists to develop this theory. All right, I think I'm going to skip to the new positron beam. This is what we just built.
Just so we know, we just have just a few minutes left before we have to turn it over to Dr. Day.
Yes, I got it. All right, I'll get it done in 5 minutes. So here's our new beam, and we just this is written up just a few months ago in Review of Scientific Instruments. Alex Weiss was the first author on that, and it shows how we get our positrons. We slow them down with a cryogenic moderator. It's but the beam is it's quite technically advanced, but it is compact. It fits in the lab, and we these coils ourselves, and the undergraduates bolted everything together. So this was built by us here at UTA. And the experiment we're going to be doing involves looking at the gamma rays coming out, not the electrons coming out this time. And the positron, when it annihilates with a core electron, the core electrons are close to the nucleus, so they're zipping around at high velocities. I mean, typically the kinetic energy of an electron, the bound electron in an atom, is close to the binding energy, and because it has a large negative potential energy, and the kinetic energy is positive. You put it together, you get a total energy which is negative, but comparable in size to the kinetic energy. So these, like in oxygen, that's a kinetic energy of 500 eV, which is for solid state, that's big. For high energy, that's nothing. But anyway, that gives us enough velocity that we can get a Doppler shift, just like the Doppler shift you hear when the siren goes by on an ambulance. If it's coming towards you, it's blue shifted. If it's going away from you, it's red shifted. If it's going, so if the positron annihilates with an electron that's going toward the detector, you get a blue shift. And our detector resolution is about 1 keV at a 511 keV, but the Doppler shift is on the order of 7 keV for some of these cores. So we can easily resolve it, and you can calculate the distribution of gamma energies you expect theoretically, and you can show that different elements will have different distributions of gamma energies. And so our idea is to inject positrons into a porous material like a zeolite. And zeolites turn out to be very important commercially. It's the basis of petroleum cracking and the refining petroleum products. They all make use of zeolites, which have internal pores, and chemistry takes place at these internal pores. And we have a way of looking at it, we think. So we're going to inject the positron into the material. It's going to diffuse to the surface of these internal pores. It's going to annihilate. The electron can't come out because it's going to be trapped in the pore, but the gamma rays can come out. We're going to do spectroscopy of the gamma rays. So to get there, we're doing the initial stages where we're looking at external surfaces. We're looking at gamma rays and Auger electrons at the same time in coincidence. Again, we're the only people in the world who can do this experiment. This shows what we got from graphene. We see the Auger electrons, and we see the gamma rays coming out, and we can decompose the gamma spectra into the different components. So it turned out we had oxygen and carbon, as well as a little bit of copper in there. This shows the new beam, and shows more pictures of the beam, another picture, and so just to summarize, we've developed surface spectroscopies using positrons, which are very highly surface selective. We've discovered new things that haven't been observed previously because they couldn't do it because of too much background or not enough surface selectivity. And we're designing a new system, or we designed and built a new system, and we've laid out a series of new experiments that we're planning on doing to develop what we hope to be extremely useful new spectroscopy, in which we use the gamma rays, the annihilation gamma rays, to study surfaces. And we hope to be able to look at surfaces which are in air and covered with gas material, because the gamma rays can penetrate all that, and maybe even look at surfaces inside of reactors or columns of fractionation columns in distilleries and so on. Yeah. So we hope to develop this technique, and I think it should be very exciting time now. We just built this beam, and we're just starting these studies, and and be a good opportunity for a student who wants to likes to build stuff and work with electronics, and we've developed our own electronics. And Randall Clayton used artificial intelligence methods to do signal analysis, and so we do a wide combination of things in our lab, and the group is not huge. It's on the order of 4 or 5 people, so every person gets an opportunity to participate in many aspects of the experiment, maybe even do a little theory. And so I would invite students to come and talk to me, and I work with Professor Koyman, and I work with Research Professor Churayev, and you're welcome to talk to them and talk to Seema, and find out my recently graduated students, Randall and Alex Fairchild. So please come and talk to us and find out what's going on. So I'll stop there.
Okay, fantastic. We don't have any questions queued up, but if anybody has any more questions for Dr. Weiss, go ahead and put them in the question section, and we'll try to get those at the end of Dr. Day's talk. So at this point, I'm going to queue up Dr. Day, and for those of you who don't know, Dr. Kaushik Day earned his PhD in physics from Brown in 1988, joining the University of Texas at Arlington in 1993. Dr. Day leads the UTA involvement in the ATLAS experiment at CERN. He proposed and built large ITC subdetectors at the large ITC subdetector at UTA, involving dozens of students, which is now installed as an integral part of ATLAS at CERN. He proposed and developed many software projects for ATLAS, primarily leading to the first worldwide cloud computing platform. Dr. Day currently co-leads all U.S. software and computing projects for ATLAS with an annual budget of over $20 million from the Department of Energy and the National Science Foundation. Here at UTA, he is the director of the Center of Excellence in High Energy and Nuclear Physics. So with that, I'm going to hand it over to Dr. Day, and take it away.
Thanks, Dan. And thanks, Alex, for that nice talk. I did not fall asleep. I was listening to it and watching it. Even though my day started at 8 o'clock in the morning with presentations to the Department of Energy and the National Science Foundation. All right, let me see if I can share my slides. Okay, I think, Alex, you need to stop sharing, or I can try to steal your share.
All right, let me see if I can stop sharing.
For sure, try to steal it.
There, I stopped sharing.
All right. I don't know if I beat you to it, Alex, or whether you beat me to it, but hopefully people are seeing now my PowerPoint presentation. Is that correct?
Yes.
Looks good to me.
All right. I'm going to go to presentation mode. On a Mac, this is always an adventure because Microsoft tries to take over the Mac totally and completely. And now we go to slideshow mode.
Looking good.
All right, thanks. And you recommend that I turn on the laser pointer, which you see on the screen now, right?
Yes, indeed.
All right, thanks. So, I will try to give you a very high-level view. I only have 13 slides. And the very high-level view is representative of two things. One, of course, the title that I threw together hastily yesterday because I was preparing for another talk which I gave this morning yesterday when Dana reminded me that I had not provided him a title. So I hope the title is vague enough that I can keep your attention for the next 15 minutes or so. What is the unknown we are looking for, and what are the future technologies that I am going to talk about? Now, let me start by motivating you for a couple of minutes about the physics. At a very, very high level, okay? If you want to learn more, know more, or want to get into any kind of depth about any of the topics that I'm going to talk about today, I will end with some links for you, and feel free to come and talk to me virtually, which is not my favorite mode of communication, which is ironic given that I, even before COVID, spent large fractions of my day on video conferencing, but it's my least favorite mode of communication. Okay, so let's start with the known. What we know today about the most fundamental description of the physical world is called the Standard Model. And this is a model which developed in the 60s based on field theory, and has led to many discoveries and Nobel Prizes over the last 50 years. But one of the biggest mysteries in the model was how to introduce mass into the field theories. And one of the proposals for introducing mass in the Standard Model was by Peter Higgs and Francois Englert back in the 60s. And it turned into one of the longest and most difficult hunt. And many people have called it an obsession in physics to find the Higgs boson, which is a particle that represents the field. We finally found the Higgs boson. It's a long story. I can do a whole colloquium on how we discovered the Higgs boson, which led to probably the fastest Nobel Prize in physics from discovery to the person who had proposed it getting the Nobel Prize in 2013. And the citation that you see on the left-hand side is from the Nobel Committee, which says that as the particle was discovered by the ATLAS and CMS experiments at CERN's Large Hadron Collider. So that's the experiment that I work in, and that's the experiment that I have been part of since the very beginning back in 1995. And when we announced the discovery of the Higgs boson in 2012, it is a new particle, and it is a very complex particle, and it has many properties that remain to be measured. And physicists will be studying the Higgs for at least the next 20 years. When you find something as complex and as fundamental as the Higgs boson, it takes 20, 30 years to measure all of its properties and figure out everything about it. In the meantime, however, one of the biggest ironies of physics is that no one really believes that the Standard Model is the ultimate description of the universe. And this is particularly surprising at its moment of greatest triumph, in that we have nailed the coffin on the Standard Model by discovering the Higgs. I mean, we have all the particles and all the fields that we need in order to have a consistent model, and yet no one really believes it is the ultimate model. So what has happened in ATLAS and what we have turned to doing in ATLAS is search for new physics. That has become the big hunt. And on the bottom right-hand corner is one of the pictures that people used to show about the search for dark matter, where you see that the visible universe is only the tip of the iceberg above the waterline, and 95% of this has not yet been discovered. And that could very well be true of the Standard Model, is that most of the mysteries of the physical universe are still beyond us and are just waiting to be found. So, to learn about dark matter, I strongly recommend, as soon as we are out of this COVID mess, to go and see a planetarium show, which we produced. I was one of the executive producers. You can see it in the UT Planetarium, and it's called Phantom of the Universe, The Hunt for Dark Matter. And it is a great introduction to dark matter and how we are looking for it at CERN. So, as I said, I'm going to talk at a very high level. And so let's jump to the specific physics topic that I'm most interested in. I've been searching for dark matter, or what one of the theories of dark that predict dark matter is supersymmetry. Supersymmetric models go beyond the standard model and postulate that there are partner particles to every particle that we have discovered so far in the standard model. And in supersymmetric models, there is a lighter supersymmetric particle called the LSB, which could be dark matter. Now, this is something that I started looking for when I was a postdoc. And for the last 30 years, I've been plagued by theorists who have just told me, keep looking for it. It is just around the corner. You will find it. You are so close to finding it. And we still haven't found it, of course. I've had half a dozen graduate students who have written theses on search for dark supersymmetry. But that's how one makes discoveries in physics. And this is one of the searches that is front and center at CERN. Ironically, if we find supersymmetry, it stabilizes the Higgs boson mass. We still don't have an explanation. We know that the Higgs field is responsible for giving mass to all other known particles, but the mass of the Higgs boson, trying to calculate it, leads to quadratic divergence, basically infinities. And one of the ways to stabilize the calculation of the Higgs mass is to postulate that there is supersymmetry. It's one of the interesting ironies. But we have not found supersymmetry yet, so we don't yet know whether or not that's the solution to dark matter or for the what's called the hierarchy problem. Supersymmetry has become very, very difficult to find. We are nowadays using the latest techniques in data science, like machine learning, in order to optimize our search. Bottom left-hand corner, I really can't go through it, but maybe I can do it quickly. It's a Feynman diagram of a possible creation of stop and anti-stop pair from proton-proton collisions, and then the stop decays into W boson, lighter supersymmetric particle, remember dark matter that I just talked about, a B quark, then the W can decay into lepton and a neutrino, and of course it is pair produced. So this is one of the many possible Feynman diagrams that can create a stop at CERN, and that's what we look for. On the right-hand side is a collection of results from the last 20 years of searching for one of the supersymmetric particles. It is the superpartner to the top quark. It's called the stop. And by the way, I was also in the experiment that discovered the top quark at Fermilab, and I remember giving the first colloquium announcing the discovery when I at UT Arlington very soon after I arrived here. So this is a compilation of all the results which show as a function of the mass of the stop versus the mass of the dark matter particle, what we call the neutralino, the lightest supersymmetric particle, and you can see how we have painstakingly with our data ruled out through various different channels the different parts of this graph. And everything that's white here is where supersymmetry could still be hiding, or actually the stop coordinate could still be hiding. Okay, so that's the motivation for the physics that we do. How do we do this physics? How do we find, or the Higgs boson, how do we look for supersymmetry? For that, we have to talk about the Atlas experiment. The Atlas experiment is the world's largest experimental apparatus. It is located 100 meters underground in a 27-kilometer long tunnel near Lake Geneva. What you see here is Lake Geneva in Switzerland. This is the town of Geneva over there. This is actually France, that is Switzerland. So the accelerator actually goes under. This yellow line, of course, is a line which is superimposed. The accelerator tunnels are, as I said, 100 meters underground, and it is so long that it actually traverses under two countries. So the border between France and Switzerland is right over there. And the main Atlas is the experiment over there, and this is the main CERN site right next to Atlas. There are other experiments around the ring. The whole goal and purpose of building the Atlas experiment is to study the fundamental properties of our universe through particles and forces. We have had, when I made this slide, it said over 700 journal publications. It's actually over 1,000 publications now. And we continue the study of Higgs, search for dark matter, look for supersymmetry, etc. What is Atlas? What do you mean by an apparatus? It really is a camera, except it's more than a camera. It's not just the photons that you get with the Atlas detector, but actually all particles. Every particle that comes out of the collision at the center of the detector and comes out of that collision, we try to measure it and capture it and create a three-dimensional composite picture of the collision event. The size or scale of it, if you look here, these tiny, tiny things, those are supposed to be people. And you can also see some people down there, tiny, tiny things. The size of Atlas is roughly comparable to what you see on the right-hand side, which is the famous Notre Dame Cathedral in Paris. Or, I should replace that picture. The Atlas is about large enough that it will fit inside the Cowboy Stadium, the AT&T Stadium right here in Arlington. It's a very fast camera. It's capable of taking a few 100 million pictures every second. And each picture contains billions of bits of complex information. So, this detector, parts of it were built right here at UTA. What you see here is the Atlas detector. And a small piece of it, not so small if you look at it in terms of the photographs here, but a small piece of it sitting right over there where the arrow points is called the intermediate calorimeter. This is a sub-detector which I proposed back in 1995 when we were designing Atlas. You see this cage. There are three people in this cage that are dangling from a crane 100 meters up. That was one of the times when I'm the person in the corner here wearing the hard hat who's trying to repair something in the detector that we built here at UTA long time ago. And there is a graduate student there, standing there, who's holding onto a rope stabilizing me. I didn't bring the video today. I've shown this video. Alex and others have seen this video. That's a graduate student with a rope stabilizing this cage hanging from a crane 100 meters up as I work on the detector repairing something just before they closed it. This is the front view of the detector, and you see two, I think that might be Dr. Yu, that's Shiley, who passed away, used to be our postdoc. That's one of our, that's Hanshin, one of our students. And by the way, I don't know if my picture is there. The background behind me is the detector that we built here at UTA, and it was built over over a 5-year period, and then shipped over. Each of these slices is the size of a person, of course. As you can see, each slice is about the size of a person. Each size weighs 1 ton, half a ton. And we build them here at UTA, and we ship them on 64 flights, because of course you couldn't fit it in a single plane, on the belly of 64 commercial flights to Geneva and installed it there. So that's what we built. But of course that was a long time ago. In order to now do the physics, in order to try to understand the pictures, what we focus on and what we do in Atlas is the most challenging task in computing, in computational physics that has ever been done. And to be honest, one of the most difficult tasks in computing that has ever been attempted, long before big companies like Google and Amazon became famous. So in order to even have a single picture, and remember, we take 100 million of these pictures every second, even to understand one of these pictures, this is a picture of an event, we call it an event display, even to understand one of these pictures coming from the Atlas detector requires an enormous amount of processing. So that kind of computing power was not available anywhere in the world 15 years ago when we first started taking data with Atlas. And so 15 years ago, what we decided to do is to take 150 different computing clusters or computing centers all over the world, stitch them together, and these are computing centers all over the world, in every country in the world, and we stitch them together, which provides equivalent today of 400 CPU cores, 500 petabytes. What is petabyte? Petabyte is 1,000 terabyte. Terabyte is 1,000 gigabytes, so it's 1,000,000 gigabyte. It's 1 petabyte. So your 500 petabyte storage is one of the largest data stores of any kind in the world. And we had to support dozens of applications, dozens of processing, support a community of thousands of users, and the software that runs all of this, that drives all of this, the software which didn't exist in those days, was developed right here at UTA. So this is the Panda software, which I am the inventor of. It was started by UTA and Brookhaven National Lab more than a dozen years ago. And it allows us to use computers at data centers all around the world, altogether, those 400,000 computers, to solve the Higgs, for example, to find supersymmetry. This is really the precursor to what we call today cloud computing. There are thousands of people who came out of high energy physics who now work at Amazon and Google, who created, and Microsoft, and who created what we today call cloud computing, which is the basis of almost everything that happens. So don't forget, cloud computing also came out of CERN, just like the World Wide Web came out of CERN another 10 years before that. So this is really the cutting edge of US innovations. And we had to do this because this was the only way we could extract the physics out of the complex detector that we had built. So just to show you a Google map of how data flows all over the world, these green lines are basically data flowing, and each of these circles are data centers, and right here at the center of this one is UTA, and this shows Google-inspired view of worldwide data movement, storage and processing, and the massive simulations that we do, and the massive data processing that we do. When in the post-COVID world, if any of you are interested, I can walk you by the data center on the ground floor of CPB, which continues to look for SUSY and play the role in the discovery of supersymmetry Today, in that room, we have the equivalent of a high-performance computing center of 10, 12,000 CPUs and 6 petabyte of data stored there. So just for fun, I thought I would include one slide from a talk that I gave this morning to JOG. JOG stands for the Joint Oversight Group. And this was the 47th meeting of the Joint Oversight Group. The Joint Oversight Group is the people from the funding agencies who ask for reports because they spend millions of dollars on Atlas. It consists of people from the Department of Energy and National Science Foundation, and I had to give a talk justifying what we do with their money. And one of the slides I just picked from my talk was something called HPO Grid, which is Panda-based distributed training and hyperparameter optimization service operating on the grid. And this shows how Panda, the software that I just talked about, which was invented right here at UTA, along with the IDDS, which is called which is a data streaming service, along with the Ray Tune library, can process machine learning training using GPUs at dozens of grid sites all over the world. And you can see a visualization of that, what we call ML Flow here. And it works for many use cases, which is for using GANs and RNNs, neural networks, and BDTs, boosted decision trees for various things, and how we achieve all of this and how we do all of this. That's what we had to explain to DOE NSF this morning in order to justify the $20 million that they spend every year for computing in Atlas. And then finally, I want to show you the title. This is from a draft of his thesis. Jared Little, my newest graduate, he just submitted his thesis last month. Congratulations to him. He's still at CERN. His thesis was searching for a pair-produced supersymmetric top partner using recursive jigsaw variables and boosted decision trees with 139 inverse femto-1 of data from the Atlas detector. He didn't find supersymmetry, but he made a valiant effort to find it. Jared is now my postdoc. He's doing his job search, and he's ready to train my next graduate student. So please contact me if you're interested in working on Atlas. Half of my team is at CERN. Half of my team is here at UTA. I have dozens of postdocs and research faculty working with me on these computing topics and search for supersymmetry. So not just Jared, but there are plenty of people who can help to train you. So if you're interested, start here. Start by visiting. Just type into your browser atlas.cern, and that will take you to this web page. And you can click on Discover, you can click on Resources, you can click on Updates, and you can learn about Atlas. We just announced a bunch of new results at the International Conference for High Energy Physics, ICHEP 2020, which was virtual this year, of course. And you can learn a lot about Atlas. And then feel free to come and talk to me if you're interested in doing this kind of research. Thank you.
Thank you very much, Dr. Day. I do want to mention that immediately following the presentations, we will be over in a different Microsoft Teams room for our virtual wine and cheese. The link went out both to the graduate students and faculty here. This is a great opportunity for graduate students to talk to Dr. Day and Dr. Weiss about the specific tasks, the different research projects going on. And for everybody else, it's a really nice time to thank the speakers of all our different colloquiums and hang out for a little bit afterwards. So with that, we have one question queued up. Oh, and a second one just hit here. One for Dr. Day that I will go first, but I'm going to warn Dr. Weiss that I have one coming his way in a second. So someone asks, are you looking specifically for stop quarks or SUSY particles in general? Also, what is the center of excellence?
Good questions. So we are looking for supersymmetry